the integration of a scalar product because it's something connected to a vector. So we do not know how to calculate the integration when there can be vectors in it. So in order to calculate this integration, we need to use the complement form. So we write it as like this. For each complement, that's a simple integration, just like one-dimensional problem. So this just like fx dx integration start from xa to xb, and here fyty means the work done by y complements, and here fzddt integration means the work done by z complements. So together is the total work. So that's how we calculated this line integration in a three-dimensional space. We change it into three integration in one dimension. Like change a problem in three-dimensional space into three problems in one dimension. So you have learned the calculus, so you know how to calculate this three. Maybe you did not know how to calculate this directly, but if you can calculate this three, the sum is equal to this integration. So we always change something we do not know into something we are familiar with. So that's how we calculate the work done by a varying force. We calculate the work done by the complements, and then we calculate the sum. If the force is not a constant force, you need to use the integration to calculate it. Okay, let's check this example. So as we know in previous equation here, we write an L. We write an L here to indicate that it's a particular path, which means the work done by this force from one point to another point, if it is along a different path, the result can be different. So the work done by F along this path and this path, they can be different. So that's why we are going to check this example. So we want to determine the work done by friction force F. We can treat it as the magnitude of force is constant, but direction maybe not. The force F is a force with constant magnitude, but the direction of the force depends on the moment. It's always in the opposite direction of the speed. So that means the magnitude can change, but the magnitude should be constant. But that means it's still a varying force because force is a vector. So we want to calculate the work done by friction force F on path AOB or ACB. But they start with the same position and ends with same position. So let's say we just try to calculate both of them, and we will compare the result and see if they are the same or not. So okay, maybe this AOB could be much easier. Because if it is moving along AOB, the force F is actually a constant force because the magnitude F, but directions B to A. So according to this fx is this f x cosine 0 is 1, and from A to B. So this part, integration of x from A to B, actually should be equal to 2r, right? 2r. So that's 2rf. So that's AOB. But if we calculate the force along ACB, that could be different. So WACB should be equal to the integration still, let's say F dot DL. And this, let's say, okay, this should be AOB. And here should be ACB. If it is along ACB, DL always in the tangential direction, right? And the force F, the friction, in opposite direction. So still integration F like so here DL, what this part DL, what's the length of DL? It should be equal to, if this radius is r, the angle is d theta. So DL, the length DL should be equal to r d theta, right? If this angle is d theta. So we just substitute into here. F DL is equal to r d theta. And the angle between this and this, so it's not in the same direction, it's opposite direction. So, okay, let's say this should magnitude, right? Should magnitude. Okay. If we choose the magnitude, right? So, this should be equal to this because cosine 180 or 100, the magnitude should be 1. Or maybe it's -1, but the magnitude is 1. So that is RF, the integration d theta, from here, which is for example, 0 to 180, 0 to pi. So that's pi RF, which is different from this. Only the magnitude. If you choose a sign, actually, they should be minus because the force and the always in the opposite direction, right? So that's why it should be minus sign. And you can see the result can be different. It should be different because they move along different paths. So that's why they for parts A, O, B. So FDL dot DL if is a constant force, so if it should be minus R2 FR. But for path ACB, the DL, the length, should be equal to RD theta. So when we calculate the integration, that's why here's a minus FDL, because the angle between these two is 180. So the integration from 0 to pi, so that's why minus pi FR. Only if we calculate the magnitude, it's 2 FR, and here is pi FR. That means along these two paths, the work can be different because the work, that means generally speaking, the work It, the work, it depends on the particular path. It does not only determined by this where it starts and where it ends. It also determined by the particular path. So that's why here is a non-integration along. That means the integration along a particular path. So and according to this example, we can see the work, the same force, the work along ACB and AOB. The result is can be different. The result can be different. Okay, so this example tells us that the work is associated with the particular path. Okay, so let's calculate another work which also frequently appears in this part. So that's the work when you press or stretch a spring. For a person to hold a spring, either stretch amount of x from its normal length requires a force Fp which is directly proportional to x but in the opposite direction. So which means the spring itself exerts a force in opposite direction, Fs, and the force due to the spring should be equal to F is equal to minus Kx. This is called Hooke's law. This is called Hooke's law. That means the force due to the spring is proportional to the change of its length and in the opposite direction. If you press this spring, the force will always in the opposite direction. So we want to calculate the work a person does to stretch a spring from its normal length. Well, XA is equal to 0 to a actual length, XB is equal to X. We want to try to calculate this. So if we are going to calculate this, we need to know this is a varying force, because when you press this or stretch this, the force will change when x changes, right? Because for different x, that's different. That's different. So the force, let's start from 0, original is 0, and when it reach x, is kx. So it is changing. It is changing. So if we want to calculate this work, we need to use an integration, and it's a one-dimensional problem only in x direction, that direction. So according to the equations, the work should be equal to like Fp. Okay, you can see in this picture, we choose this to be x, and this is 0. So that means Fp and dx, they are in the same direction because it's stretched, right? So x increase. So that's why it should be equal to Fp dx, which is also equal to the integration kx dx, let's say from 0 to x. And this gives us the result half kx squared. That's the work done by this person when he stretches a spring from 0 to x. From 0 to x. So that's the work done by the person. So at the same time, what's the work done by this spring? What's the work done by this spring? So the work done by this spring actually should be minus half kx squared. Because the force is in the opposite direction, if you want to calculate work done by the spring, you should use minus kx instead of using kx here. So that's why it's minus half kx squared, the work done by the spring. So that's the same amount but different sign. Okay, so now we know if it is a one-dimensional problem, we can use the integration to help us to calculate the work done by this varying force. So let's check this one. A robot arm that controls the position of a video camera is automated surveillance system. It's manipulated by a motor that exerts a force on the arm. So the force is given by this equation, and well, F0 is equal to 2.0 Newton, x0 is 0.0070 meter, and x is the position of the end of the arm. So if the arm moves from x1 is equal to 0.01 to x2 is equal to 0.05 meters. So how much work did the motor do? So someone said he doesn't understand which part. He doesn't understand which part. So the equation, which equation? You mean this equation? Or the equation in previous slide? Okay, this equation. So this equation, maybe we do not know where it comes from. It is just the equation like how the motor works. It's just like a program inside this motor. Just like a program. It is programmed to work like this. This device is programmed to work like this according to this equation. It can apply force according to this equation. It is programmed. It's a robot. It's a robot arm, and the force is programmed to work like this. So is that clear? So it's not a physical question. It's not something in physics, just like a program that controls the works. Okay, you wanted the previous slide. Okay, which equation? This one or this one? So okay, let's say the second one. This one, right? This part, right? Okay, so I can explain this again. Let's move all this. Remove all this. So okay, let's redo this part. So we know. So this force or this force, according to Hooke's law, this force on the spring should be proportional to the change of the length. So that's why here these two equations. And then if you want to calculate the work done by a variable force in x direction, let's choose this equation. So the work done by a varying force in x direction can be calculated with this equation, the integration of the force along x direction. So that's why here, the work done by the person, the work done by this force, like this is the Fx, right? So Fpx dx. Integration start from here to here, from 0 to x. We substitute this equation in here. That's the integration kx dx. The negative sign for opposite direction, yes. So here, negative sign, that means in the opposite direction, because we choose this. If we choose here to be x, if fp is positive, that means fs is negative. Okay, so let's go on. So this arm is programmed to work this according to this equation. So now we want to calculate the work done by the motor. It moves this from x1 to x2. So this here is a varying force in only x direction. So the work should also be equal to fx dx and integration. Like start from x1 to x2. And fx is given by this equation. You can substitute it into this and calculate the result. So maybe you can try to calculate it by yourself first. Try to calculate this by yourself first. Okay, I can give you several minutes to calculate it by yourself first. Okay, let's take a rest. So this is the second time. Okay. Okay, so let's go on. So the integration, fx dx. So we substitute the x into the equation for fx into this equation, and then integration, and it's x squared. So that's why here is x cubed. So and we substitute the values into this equation to the work. So this is the one dimension. So integration can help us. The integration can help us. Sometimes there can be several forces on one object. So the work done by multiple forces or by several forces should be equal done by the individual force. So that's just the summary, just sum of this force. Okay, someone said, okay. Okay, so that's okay. So as we mentioned, this is this half mv square is called kinetic energy because it's the energy associated with the motion of the particle. So half mv square is called kinetic energy. And the work done on to change of its kinetic energy. We have just get this equation at the very beginning because at the very beginning we know that equation. At the beginning of this chapter, if you remember, we have this question: half mv one square v2 square minus half square is equal to Fd. So Fd is the work. So this is a change of its kinetic energy. So that means that net work done on an object is equal to the change of its kinetic energy. And this is called work. This part, maybe it is a work done by constant force, and it can also be a work done by a varying force. But no matter it is done by what kind of force, it's the work, it's the net work. The net work done on an object. This delta K means the net work. But delta K means the change. Delta K means the change of kinetic energy. W is the net work. The net work is equal to the change of kinetic energy. So this can help us to calculate this. We work on a car to increase its kinetic energy. How much net work is required to accelerate a 1,000 kilogram car from 2 meters per second to 30 meters per second? So how much work is required? So the work required to accelerate this is that means we do work to increase its kinetic energy. So the change in kinetic energy should be equal to half mv square minus half mv zero square, and this is the work, and the mass is this. V is 30, well, V0 is 20. So it should be equal to the work required. That should be equal to the work required. So let's see. Okay. The work required is large. Work required. You may for example, if not 20, I want to double the speed. If double the speed, that means 4 times the kinetic. So that's why accelerate a car. It's not so easy. It requires extremely large energy because you want to double the velocity. The kinetic energy should be 4 times, not 2, because it's v squared. It's v squared. Okay, so then let's try this one. A car traveling 60 kilometers per hour can brake to a stop within a distance d of 20 meters. If the car is going twice as fast, for example, 120 kilometers per hour. So that's the maybe the speed on the highway, right? So what is its stopping distance? Assuming the braking force is the same. So if the braking force is the same, and we can treat it as a constant force, so the work done by this force should be equal to F times the distance. For example, the braking force is F, and the stopping distance is D. So FD should be equal to the initial velocity is 60 or 120, and the final speed is 0, right? Because it stopped. So stopping distance, final velocity is 0. So equal to 0 minus half mv squared, which is also equal to minus half mv squared. So if this one is doubled, and this should be not only double, but 4 times. So maybe you can calculate by yourself first. What's the stopping distance when you double this speed? Try to calculate this. Okay, here if it's 6 kilometers per hour, it's 20, and if it is 120, when you double the speed, this should be 4 times of its original. That's why it is 80. It is 80. So that means when you double your velocity, the stopping distance not only doubled, but 4 times as its original. Because the stopping distance is proportional to v squared, not v. It's proportional to v squared. So that's why on the highway, if there's something wrong with your car, you stop it and you need to put something after your car a much longer distance than that you are original road, the regular road, right? So that's because the sloping distance is much longer. So you need to let the others know earlier there is something in front of you. Okay, so next section is about the conservation of energy. So in this part, we after finishing this chapter, we are expected to be able to do following things. So that's what you can achieve after you have learned all this. So you need to know how to interpret the main features of conservative force and non-conservative forces, and describe the relation between potential energy and conservative forces. To determine whether the mechanical energy of a system conserves, and apply the law of conservation of mechanical energy to real problems. So that's the only objectives of this chapter. So the content about this are conservative forces and non-conservative forces, and the potential energy, and also conservation of mechanical energy, and the application of this law of conservation of mechanical energy. So, according to previous chapter, the work is associated with the particular path, but the work done by some special forces, it does not connected or associated by the path. For example, the gravity. Let's say if it is moving along this path, not straightforward, not falling straight, not this, maybe it's not a free fall. So the path from A to B, and maybe you will find out that the work done by this force depends only on the position, not the particular path. Is this part or start from here to here? It's the same. Depends only on the y, the coordinate y. So it depends only on the position, relative position, but not on the path. And this is not the only one. Maybe there can be many other, not that many, several forces. They are special. The work done by this kind of force, they depends only on the initial and final position, but not on the particular path. And this path is this force. They are called conservative forces. The work done by a conservative force on a moving object from one point to another depends only on, there. Only on their initial and final position. Only on the position, but not on the path. And these forces, they are called conservative forces. For example, gravity and gravitational forces and elastic force. Like for example, the elastic force, we know this. The elastic force, the work done by this is half x squared. It depends only on x, right? Not on the particular path. And electrostatic force, we will investigate the electrostatic force in the following chapters. And if the force is conservative, so when work done by conservative force on an object when it moves along a closed path, the work should be zero. Electrostatic. So, someone asked, what's the electrostatic force? For example, here is a charge at rest, and then you put another charge here. The force between them is electrostatic force. Is electrostatic. That means the force due to a charge at rest, not a moving charge, the charge at rest. Static means at rest. The work done by conservative force. So, for example, here, it starts from A, then to B. The work depends only on the position of A and B, does not on the path. So if it does only on A and B, if it goes started to A and B, then back to A, It goes back to its original position. The initial and the final position is the same. That means the work is zero, because it's the same as if it does not move, because it's only on the position, not on the path. So that's why the work done by a conservative force on an object moving along a closed path should be zero. And there should be also non-conservative forces. The work done by a non-conservative force on an object moving from one point to another depends not only on the position, but also the path, just like the friction. We have calculated this in previous section. The work done by friction definitely will be affected by the particular path. So we call this kinetic. Well, maybe I should use the same name. The kinetic energy. The kinetic energy and potential energy. So we know what is kinetic energy, half mv squared. So if originally I put something at rest here, and then I move it up slowly, and then stopped here. So stop it here. The kinetic energy at here and here should be the same, and they should all be zero, because the speed is zero. But you know, when I raise this, I move this from here to here. Actually, I do work on this object, right? But according to work kinetic energy theorem, if I do work on this object, I will increase its kinetic energy. But actually, the kinetic energy does not change. So why it does not change? Why it does not change? Or what changes? Okay, so if I release the ball, it will fall freely. It will fall freely. It will fall freely. And it go back to here. The kinetic energy will no zero, and it should be equal to the work done by me moved from here to here. So It's no longer zero. It seems that when I moved from here, from A to B, I did increase something. It's just like maybe I have increased its kinetic energy, but the kinetic energy is stored in the ball. It does not show itself. Just when I release it, the kinetic energy show itself to us. So, called potential energy. Why we call it potential energy? When I moved from A to B, I did increase something, and this energy is just like this object. The hidden energy in this object, it has potential to change into kinetic energy. So why it's called potential energy? Because it has a potential to change into other energies. So that's why we call it potential energy. When I move it from A to B, what I increase is the kinetic energy. Is the potential energy, not kinetic energy. Potential energy, not the kinetic energy. So potential energy is the energy that associated with the position and the configuration of the system. So it's different from kinetic energy. So just like here, when I move it from A to B, I increase its potential energy. So this is just like the kinetic energy inside this system. And usually, in this case, this is called gravitational energy. It's equal to the weight times the height of this relative height of this object. So this is called gravitational potential energy. So this gravitational potential energy depends on the reference frame and where it is choose to be zero. Usually, we can choose where y is equal to 0 to be the position where the potential energy is 0. So that's why, yes, it's a quite complex theorem, but what you need to understand is the conclusion. How to get this step may be complicated, but for you, you are not majoring in physics, so you only need to know the conclusion, like this equation. How to calculate the potential energy? You just use this equation and choose C is equal to 0, which means you choose where y is equal to 0 to be the 0 position of the potential energy. So we assume u is equal to 0 and y is equal to 0. Then we can put c to be 0. So then the equation is simplified. Uy is equal to mgy. That's enough. Uy is equal to mgy. The potential energy is equal to mg times the y coordinate. If you choose the y is equal to 0 to be the 0. So let's check this. How to calculate the gravitational energy. So, okay, a 1 kilogram roller coaster car moves from point 1 and then to 2 and then to 3. So what is the gravitational potential energy at 2 and 3 relative to point 1? That is, choose y is equal to 1 at point 1. So if we choose here, oh, sorry, I hit the choose. Okay, so if I choose here to be the origin, and in this case, y2 should be equal to like 10, right? 10 meters in this case. Then for step A, right? And y3 is equal to, if here is 0, here is minus 50. Minus 50. So the potential energy at here, y2 is equal to mg y2. In here, y2, you should use 10 meters. That's, let's say, U2 or U3, the potential energy at 3 should be equal to mgy3. Well, here is my y3 is minus 15. Okay, so what's the change in potential energy from 2 to 3? That is equal to U3 minus U2. Okay, then let's repeat parts A and B, but reference point at point C, if we choose here, point 3, choose here to be the origin, then in this case, y3 is equal to 0, while y2 is equal to 25 meters. So y2 and y3, they will not be the same. They will not be the same. So you will get different value. But the change is the same because the change depends on the relative difference between these two. So if we can also compare the result. So the first part, U2 is equal to mg2. If we choose 0.1 to be 0, as we mentioned, it should be 10. For y3, it should be minus 15. And that's the potential energy. And the change in potential energy is equal to U3 minus U2. So that's A and B. So let's see if we choose y3 to be 0. And in this case, you can see U2. It's different from this one, right? It's different from this one. But the change is the same. So this example tells us that the potential energy depends on, well, you choose to be 0. For the potential energy at the same position, if you choose different position will to be 0, the potential energy at all, even at the same position, can be different. Just like here, potential energy for point 2, if we choose y3 to be 0, it's 2.5, while we choose y1 to either this is 9.6 times 10 to 4 and it's 10 to 5. It's not the same. That means the potential energy, even for the same position, it depends on where you choose to be 0. But if we check this, these two are the same. That means the change of potential energy does not depend on where you choose to be 0. The exact value of the potential energy depends on where you choose to be 0, but the change of potential energy does not depend on where you choose to be 0. So that's about the potential energy. Okay, maybe you can stop here today. Still here today. So class is over. So see you next week. Yes. You have So which part? You mean? So okay, I know. Okay, a book. I have sent the link to a LED disk, and there can be. You want the solutions for the solution of the examples, or you mean on the books or on the you mean the examples on the book? Okay. If it's an example, there should be a solution on that book. But if you mean the questions on that book, maybe not. Maybe not. There may be no solution to the questions. No solution to that question, to all the questions. Only the result. Not there's no detailed solution to the questions. Only result, not no solution to the questions. There may be a student manual for this, but that is not the same version. So you need to compare the student manual and the book and try to find out which one corresponds to which one. But maybe you can do this, but but for you maybe you can, if you can deal with all the examples, that's enough. And for the questions at that book. But if you want to find out the a detailed solution, maybe that's not possible. I can provide you another the student manual, but it's not the same version. So you need to find out which one corresponds to which one, which solution corresponds to which. Okay, I can provide that book. I can provide that. I can provide you that book. I will send it to the group. I will send it to the group. Okay. Okay. Bye bye.